Hi, my name is Samay Patel, and this is my Physics 2211 Constant Velocity Lab Report and the findings that I took from it. So to start off this report, the goals of this report were to analyze the position of an object at constant speed which is supposed to have no change in direction, and create an experimental computational model using tracker, and then using the velocity from the tracker, we were supposed to create a theoretical computational model using Newton's second law. And then the final objective was to determine if there were any discrepancies or differences or similarities between the experimental and the computational model. So for some background information, the concepts and equations of Newton's second law must be discussed and understood. So in this lab, the understanding is that the change of velocity only occurs if there's a net force acting on it. However, since this lab is at constant velocity, we are assuming that no force is technically acting on it. So the equations, obviously Newton's second law, V final is equal to V initial plus F net over m times delta t, and since no force should technically be acting on it, F net would be 0, it should be V final is equal to V initial. In this case, also for average velocity is equal to change in position over change in time. But if assuming constant velocity, then V final should obviously be equal to V initial. There should be no change in velocity. And so if we're calculating position, the position final is equal to position initial plus plus velocity times delta t, since no net force is assumed. So for this experiment, the first part of it included finding an object and recording a video of it moving at constant velocity. In this case, I chose a water bottle. And then using the application tracker to obtain an experimental data position compared to time. Using this data to create an experimental model of the data, use the provided GLOW script in order to create theoretical models and compare the results of the models to each other. So after using tracker, this was the model that we came up for the experimental data. And this was the code that we made this was the code that we used to make the final velocity values. As you can see, this is the velocity value and this is the initial position value. Obviously, vector in this case would be 0 for F net because there's no force acting on it. Now this is the theoretical model using initial velocity. This is what I used from the first condition and this was at the first data point. And using this was the model that we used. Now this is the theoretical using the final velocity. This is the initial condition and these are the final conditions. Obviously there's a big difference between this and the initial one because this one is at 2.35 seconds. And obviously the velocity is much lower than it is for the initial model. So if we compare the models, each of these have one copy of the experimental data on it, and each of them also have a copy of the theoretical and then the final. The theoretical, in this case, would be the initial and the final. As you can see, there's a lot more difference in the initial and then the final. And that's what I expand more upon here. With the information regarding the comparison models, the final velocity model is obviously better. Since the velocity in this case accounts for every single data point and not just the first two, it accounts for the whole data better and it creates less variation in the model. This also, it's like this, and you can see this in the difference in the initial velocity and the final velocity, as the initial velocity is more than double the final velocity. So using Second's law, these are just some observations and conclusions. Velocity is constant as there is no force involved, but as we can see, there's a difference between the initial velocity and the final velocity. There were forces acting on it. This is most likely due to the slowing down of the water bottle due to the force of friction on the surface. And since it was on a level surface, there is no gravity involved. Now, what if? Now, we made a choice for the orientation of axes on these models. Now, obviously, the question was what would change if you were to flip the axes from negative x to positive x? Well, in this case, since position is a vector, it has velocity and direction. So changes x-axis would cause a change in the direction of values. However, for force and velocity in this case, we are considering scalar values, so direction is not important. And for the observations, if we set the net force equal to 0, how many net forces would we see on the overall object? I considered only 2 forces, from the force of the push and from the force of the friction. That was the only ones that I considered on the object. Thank you.